machines will turn their lights off if there's no motion arm for 5 minutes or so, and then when you walk by, they fire back up.
Fred Myers does that too.
It's genius. Number one, it saves power. Number two, it gets your attention.
Sure.
You walk by, and you just, all of a sudden this thing goes, and the lights come on, you're like, ooh, I suddenly want a Coca-Cola. It's genius, because it saves power and it gets your attention. It's a win-win, in my opinion. Genius. I like the Rumble Strips. I like the Rumble Strip version of convenience store machines. We got data, yes? Let's fill in some templates. So have two of them out in front of you. Have two of them out in front of you. There's a lot going to be similar between the two of them. There's going to be a lot similar between the two of them. I mean, pretty much everything except, I'm assuming, the test statistic and the p-value. I'm guessing that's going to be the differences. But they're going to have very, very, very similar results for the two of them. Which variable are we testing in each?
Mu.
Definitely mu in each one. Definitely mu in each one. What is the variable that we're testing? Mu, in context, what is it standing for? Exactly! Average speed of those cars! Yeah, that past that road, I guess, if you were to be more specific. But yeah, the average speed of the cars. Say that again?
That'd be for both of them, right?
For both of them, yeah, that's what I'm saying. I think a lot of these are going to be exactly the same. Honestly.
And you would say recorded by individual, recorded by...
You could, but I wouldn't, because both the police and... Did you hear what the Ann said? It's a very, very good point. She said maybe we should differentiate for each of the things. This is recorded by police, this is recorded by the individual. They're both interested in the same thing. How fast are the cars going on average? Oh, I would just put that up on top of a quiz somewhere. Yeah, I like what you're saying. I like what you're saying, but check this out. You're not going to need that once you get down to step 7 and 8 and 6. Because you're going to know which one was the cop versus the neighbor based on the size of the p-value. I guarantee. Oh, of course I would. Of course I would. But I'm saying you're not going to need that. Because of the central limit theorem, you're not going to need that later on. When we get down to it. Fair?
Fair.
Fair. Thank you. Okay. I think that's some hypotheses to define involving mu. Mu. We see this? Maybe. Oh yeah, we can. It's not bad. Okay. What are we trying to see?
Greater than 30.
Good, Stacy. Where's that go?
H1.
Nice. We're trying to see if we exceed 30 miles an hour. If the average speed of the cars is greater than 30. Love it. What's the research? Excuse me, what's the null? Damn it. Good, thank you for looking at me like that, Megan. We just said the research. What's the null hypothesis? Less than or equal to, but they're not exceeding. Good, I like that. I like that. That's an interesting way of putting it. I never thought about that. You could just do this.
Yeah.
You could just do that, if you wanted to, I guess, couldn't you? Maybe?
Is that science? Is that like...
That's legit. It's not greater than, which would be less than or equal to, right? Not greater than, it's less than or equal to.
But if we did that in another class, they'd be like, what?
They might not, they should have no problem with it mathematically, but they might not be used to seeing it. Your call.
Sean just did Sean thing.
No, it's not mathematical, simple. Yeah, it's not mathematical.
Okay.
Sean thing. That's full Sean things. The part where it could get tricky, and this is understandable, is if this were a two-tailed test and this was not equals, you'd have to go equals up here, because not equals looks too weird. It's like an equals with an X through it, right? So it's not a short thing though. It's just a very uncommon mathematical symbol.
Okay.
Good enough. Okay, so I drew a curve. I drew a curve over here. I put 0 in the middle. Fair? What contextual number should be at that 0? Because we're comparing it to 30, yes?
Yes.
There's a 30 right there. The question is, what is our sample's average? It looks like, according to Michael, and I think according to it was Harrison actually. Harrison, and I think somebody else agreed with him, it looks like they are going a little faster than 30 on average. It looks like that, doesn't it? Based on where the graphs are, although I didn't give you graphs, did I? Kind of a bastard, I didn't give you graphs. Let's take a look at some graphs. Let's take a look at our data, a smidge, yes? We'll look at the neighbor's data first. Neighbor's data first. L1, L2 is probably golden. No problem with that. Zoom stats. Okay, there's the neighbor's data. Finagle the window a smidge. I'm going to make it go, it goes 15 to to 50, so I'll go 15 to 55 by 5. So there's the neighbor's data. According to it, there are no outliers. So nobody's going excessively fast, nobody's going excessively slow. It's kind of an incomplete bell curve. A little bit of skew. This little guy out here, this little hiccup out here is not unusually big. It's the largest value, but not unusually big.
What do you mean by excessively fast? Because more than half are going over the limit.
Well, excessively by measure of outlier. Nothing showing up as a statistical outlier. Good, that's a very good question. I mean, excessively fast, is that significantly 244 significantly? I'm just testing to make sure I can actually legally put my data into this test I'm about to do. Is that fair? Did everybody catch the answer question? It was a very, very good one. I said nobody's going excessively fast. She asked a very good question. What do you mean excessively fast? Why that's such a good question is, we're testing to see if the average speed of the entire group appears to be over 30 miles an hour. But I don't want to have one data point maybe compromise the study because it itself is too big. So that's a fantastic question. So in this word, I'm looking for outlier data points that might pull the average. Thank you for that question. So there's the neighbor's data. Real quick, I'm going to check the COPS data. So all I'm going to do is I'm going to go into my stat plotter and change the L1s to L3s, or excuse me, the L2s to L3s. I'll get the same graph, but it'll be the COPS versus the neighbors. Here's L3. Okay, it's shrunk down a little bit more, which hopefully makes sense. There's not as many data points in the neighbor's curve. But again, nothing outlierish in the data. So I'm happy. If you want, I can make the Y scale or the Y max a little bit smaller. Maybe make it 12-ish. So again, roughly a bell shape. It even has the same little hiccup like the COPS did. Maybe it's the same car. Who knows? Could be the same car if the cop and the neighbor are measured at the exact same time. Chances are they're not. A lot of times, I used to have a neighbor that did this back on the East Coast all the time, where he would complain. The same road my cousin used to stop on. I mean, it was a busy road. I'm not claiming that her claim had no merit. It's just an opinion. My neighbor would actually go out. I think I told you guys the story before. He would measure speeds with me. Like I was doomed to be a statistician from day one. He would send me down 200 feet away, and he would raise his hand, and I'd start a stopwatch, and then I'd stop it when the car came by, and he knew the distance, he knew the time, he was doing the conversions to miles per hour. Then he'd collect data and send it to the cops and be like, look, this is what I'm charting. He's basically sending them graphs like this. So I mean, this can happen, and then if you get enough legit data, the police will then take action on it. But just hearing a person go, people are going down fast on my road, well, that's an opinion. But if you give them, here's my results, assuming that you're not lying to them, here's the results I measured, then they'd be like, okay, this is a citizen that actually cares about safety, maybe. Does that make sense? Yeah. Okay, good. You can do this too. I mean, this is nothing secret about this stuff you can do. Okay, so I think our data is good to run, yes?
Yeah.
Good. So, done with that for a second. Let's identify the errors. We've got our data. It's ready to run. But before, let's take a pause. Talk about the ways we can be wrong. Stace?
Claiming that people are speeding when they're not.
Claiming that people are speeding when they're not is a type 1. So a type 2 would be claiming they're not speeding. Speeding does not occur when in fact it does. Your vote for the worst of those two. Vote for type 2. Tell me why?
Because people can continue speeding and cause an accident.
Yeah, and maybe even escalate. Who knows, right? Maybe even escalate it from that. Good. So type 2, we don't like type 2. Anybody else not like type 2s? Anybody not like type 1s? Go ahead, Dan. Why?
It'd be like the boilerplate stuff, and they'll start to, right?
Yeah, perhaps over-regulation. You gotta realize too, friends, a type 1 and a type 2 cannot exist at the same time. A type 1 is a positive test result, a type 2 is a negative test result. So you're not gonna get both. But you do wanna look at both. And the reason you wanna look at both, I'm gonna close the class with the reason you wanna look at both. I'm gonna have a quiz next week on error, should you choose to do it. The reason you wanna look at both is, depending on which one you want to minimize, you can adjust confidence to help you minimize it. Now, this doesn't make any sense verbally. 0 sense verbally. I think graphically it'll make a whole lot of sense for you though. So right now, it looks like we don't like type 2 errors, or we don't like type 1. Show of hands, just curious. Who says type 2 is worse in this case? Type 2 is worse? Not half the class? The rest of you say type 1 is worse?
Yeah.
Okay, so about half and half. That's totally fine. Totally fine. Depending on which one you think is worse, we'll see how to control for that. again, it's one of those over and above analyses, but I also think it's very, very important to understand why they operate independently and oppositely. Good! We ready? Which distribution we using? Definitely a t-distribution, because we're testing average in both cases. And now I believe it's time we see if these cars are speeding statistically significantly. Let's find out! Let's test the neighbor's data first, shall we?
Yeah.
I think so. I think data's the way to go, yes? Everything's ready to go-ish. Gotta change the null to 30. It can get everything it needs from the list and the frequency. Yeah, we're good there. We're trying to see if it's exceeding. Love it. You guys like draw or calculate? Draw, me too. Me too, here it comes. Now somewhere over here is this 5% we're shooting for. Alright. How we feel about, there's a little bit of area. Okay. So for the neighbor got data about 2.4 standard deviations away from where it should have been. Right? Which carries a pretty small p-value, less than 1%. That's for the neighbor. You want to just finish this one off and then go back and do the cops data?
Yeah.
Just finish the neighbor, yes, finish the neighbor's test and then go back and do the cops. So let's just put the cops aside for a second. We've now got 7 and 8, yes? 7 and 8, 2.4, and less than 1%. So what do you think of number 9? What do you think of number 9? It appears, Michael, go for it!
Cars are going significantly faster than 30.
Boom! It appears the cars are going significantly faster than 30. Which then opens the can of worms for the experts to decide what? How much faster they're going. Let somebody else decide that. That's not our job to decide. Our job was to decide statistically significantly, is the average above 30? Not practically significant, statistically significant. Very nice. Could we have made an error?
Yeah.
Of course we could. We could always make an error. What type? What type? Okay, there it is. I started a little bit of this tension, very quiet. Type 1! You get a small p-value, it's always a type 1, yes? It's always a type 1. It's a false positive, potentially. Potentially a false positive. You're saying they're going too fast. Maybe they're not. Maybe you got deviant data, right? Maybe you got deviant data. I'm curious. I'm going to run something real quick. I'm going to run one bar stats on L1 and L2. Okay, the neighbor's, now check this out. The neighbor's sample has an average of about 32 miles an hour. Leading people to say, what the hell? 2 miles over? The cops will give you 9. Time out. Not practical significance, just statistical. The average has shifted statistically. Fair? Now let's test the cops' data. We good with that one? We're happy with that hypothesis test? I'm almost sure myself knew what's going to happen. Happy with the neighbors?
Yeah.
Go to the cops. So we're still at step 6, I guess. We're still using a t-distribution. Rerun the test again on L1 and L3. That's the cops' data. Same exact test.
Do we have an answer for number 5?
Number 5.
Which one we think is first?
I don't think so, because then you're making your decision based on who's collecting the data, which is not what I'm after. I'm after the result of the experiment, not who's collecting the data.
Earlier I was saying type 1 because the police will ignore you. So if it's the police collecting data, I would give it.
Oh, I'm sorry, I misunderstood what you said. I thought you meant a type 1 would result in more
It's the one first.
superfluous intervention. I misunderstood. I don't want you concerned about who's collecting the data. That's irrelevant. I'm assuming whoever's collecting is collecting it correctly. I'm concerned about the reaction that your result will cause. So a type 1 error, in your opinion, is worse. Not because the cops will ignore you, but because maybe you will make the cops come out unnecessarily, thereby pulling them away from something else they should be doing. That's one way of looking at type 1 here, right?
But that could be continuing later on.
Yeah, but I can't measure that. I can measure a type 1 error. I can't measure the cop's feelings towards you later on. And see what I'm getting at? I'm trying to limit it to only stuff we can actually measure statistically. Fair? I'm not trying to be a bastard. I'm just saying I can't measure that, so. Here we go! Everything's good except for L1, L3. Everything's the same, yeah? Let's do it! What do the cops have? Oh! Holy crap! Well! Well. Well. What are the cops gonna tell you?
That is not spend no money.
Cops, nobody's speeding. They're only a half a standard, I don't know what the cops are gonna say, it's a half standard deviation away, but their data is only a half a standard deviation away where it should be, which is well within the confines of everything allowable in statistics. Huge p-value, plenty of agreement with the null hypothesis, 29%, that's humongous, yes? Humongous, way above 5%. I'm curious, I'll be right back to this.
But you talked about this earlier, I mean, their average is very similar. But
That's what I was gonna check.
because they have so many smaller, or
Such a
a
small
much smaller
sample
sample size.
Yes!
It brings it.
Yes, Michael, and you've got the exact, notice the test statistic is still positive, just like the neighbor's was. That means it's above average. And this is one of the criticisms of hypothesis testing, just so you know. This is a criticism of hypothesis testing. One criticism is, you can make anything look significant if your sample size is large enough. You can make anything look significant if your sample size gets big enough. Notice how their averages were almost identical in the sample, 31.1, 31.2, but in one of them it was statistically significant by virtue of the fact that we drove the sample up so high that the standard error shrunk down. So eventually, if you make the bell curves tall enough and skinny enough, they're not going to touch. Even if they are touching originally, think about it this way. Here's a bell curve, here's an alternate bell curve. Not touching, right? But even one that's here can be made not to touch if we increase the sample size to such a degree that they both suck in and head up. Then they're not going to overlap hardly at all. So that, Michael, you just brought up one of the main criticisms of hypothesis testing is that with a large enough sample size, you can make any effect meaningful. Statistically meaningful, not practically meaningful. That's the experts again. Lauren, you were going to say something back there. Something was bothering you.
Isn't that just redundant? If you get a higher sample and more people in that sample have whatever you're testing?
It's mathematically redundant in a way, but here's my counter to that, my non-mathematical statistical counter. Suppose you did the COP sample and got no significance. So you say, let's get more data and see if we can force significance. Very rarely are you going to go capture more data and have the average stay exactly the same. It's most likely going to change too. So very often we'll talk about mathematical differences in the variances, but the centers are going to shift too, most likely. Just like our Iraq data did, remember? Our Iraq data in your class was centered right around 20%. Then you went and got more data and it went to 60% with more data. So the standard error went way down, but the average went way up. So, I mean, realistically speaking, you're not going to stay right there while your curve gets tinier. What I'm saying though is, given any change, mathematically, you can derive a sample that will make it meaningful. Is that fair? I love your point. It's a very, very good mathematical point, but statistically, it doesn't seem to happen very often. Is that fair? Now, I do want to talk, especially because you guys were kind of mixed on this, about these types of errors. Everybody happy with how the COPS is not, it doesn't appear that the COPS are indicating speeding? What kind of error could the COPS have made? They're type 2, aren't they? Because they're saying they're not speeding.
But it's still positive, so that it doesn't...
No, the test statistic is positive. The test itself is not. The average is higher than 30, but it's not statistically significantly higher.
So that's what I wrote. It appears that they are speeding, but it's not statistically significant.
Then it does not appear they're speeding. I see, Sharon, what you're doing is you're ignoring the whole test. You could have gotten that conclusion back at step 1 when we graphed the data and ran one of our stats. You have to put it does not appear they're speeding because that step 9 is a result of the step 8 before it and the step 7 before it. Big p-value does not appear. The average, I see what you're saying. What you're saying is well taken. But if you say it that way, you're ignoring the test and you're only looking at the sample. The test is allowing you to take the sample and stretch it into the population of all the cars.
Well, it doesn't appear that they're significantly speeding.
That's the conclusion that we need to write down. It does not appear that the word significantly can or doesn't have to be in there. It's implied. If you say it does not appear that they're speeding, it doesn't appear they're speeding significantly. Even though the sample shows a slight increase in speed over 30 miles an hour, it's not a statistically significantly increase. It's a statistically significant increase. Is that fair?
Yeah.
We'll get used to...
miss this later
No, you're not. I'm recording it.
Okay.
Okay. Now, I want to talk about this error. That was a type 2 possibility, yes? That was a type 2. I want to come back and chit-chat about error briefly with you guys because I keep saying things like, which type of error do you think will be worse, type 1 or type 2?